JavaScript was originally designed to add simple interactivity to web pages, but modern web applications demand near-native execution speeds. The V8 engine has a clear performance mandate. Take a highly dynamic scripting language and execute it like a compiled, high-performance application. Because JavaScript is dynamically typed, the machine doesn't know the exact memory layout of an object ahead of time. In a naive execution model, every single property access requires an expensive hash table lookup. To bypass these inherent inefficiencies, V8 operates as an adaptive virtual machine. It observes how your code behaves while it runs, identifies predictable patterns, and speculates on future operations based on those observations. The compilation pipeline begins when the engine receives your source code as a stream of raw UTF-16 characters. This text is fed into the scanner for the first stage of execution, lexical analysis. The scanner systematically reads through the character stream, grouping raw text into meaningful units called tokens. It categorizes operators, identifies variable names, and isolates distinct literal values. Next, the parser consumes these tokens to construct an abstract syntax tree, or AST. This process translates the flat sequence of text into a strict hierarchical structure, creating a set of logical relationships the engine can actually analyze. But parsing every line of code immediately is expensive. V8 uses a technique called lazy parsing to save startup time. For functions that aren't called immediately, a pre-parser skips building the full AST. It only validates the syntax and records the function boundaries and closure data. By deferring the heavy lifting until a function is actually invoked, V8 prioritizes fast initial execution. The engine intentionally delays complete code comprehension to ensure the user can interact with the page as quickly as possible. With the AST generated, the engine has a logical map of the code, but it still needs to connect those variables to physical memory. To do this, it establishes a lexical environment. The engine organizes the program into execution contexts. These are the strict logical boundaries that dictate exactly which pieces of data are accessible to the code at any specific moment of execution. During this initial scope analysis, V8 uses a symbol table to track these bindings. It actively maps the text identifiers you wrote in your script to the precise hexadecimal memory addresses where the data will actually live. This mapping becomes complicated when a program creates a closure. A closure occurs when an inner function continues to reference a variable that was declared in an outer scope's lexical environment. This creates a direct mechanical conflict. Standard local variables are stored in stack memory, which is automatically cleared the moment a function finishes executing. But a closure dictates that the resonance data must survive long after that outer function returns. Stack memory is incredibly fast and efficient because of its predictable lifespan. Heap memory, by contrast, is much larger for long-term persistence, but carries heavier overhead. To resolve this, V8 identifies which variables are captured by closures. It detaches those items from fast stack memory and migrates them to the heap, ensuring accessibility. Closures force the runtime to make a structural compromise. The engine deliberately trades stack efficiency for heap persistence, strictly to maintain the lexical integrity of your code. Once the memory boundaries are set, the engine moves to active execution. The AST is translated into bytecode, which is the native language of V8's interpreter, Ignition. Ignition operates as a register-based virtual machine. It utilizes a dedicated accumulator register to hold intermediate values, which keeps the generated bytecode sequences short and highly efficient. But as Ignition starts executing, it hits the core bottleneck again. Finding the physical location of properties on dynamic JavaScript objects requires slow hash map lookups, costing dozens of CPU cycles per access. V8 solves this by dynamically assigning a hidden class, internally known as a map, to every object. These maps observe the dynamic properties and simulate a rigid struct layout, similar to compiled languages like C++. The map records exactly which properties exist and maps them to fixed memory offsets. This turns a complex search into an O1 memory load. Instead of hashing a string, the engine reads from a predetermined memory address. Objects rarely stay static, so maps form a transition tree. When you add a new property, V8 spawns a transition to a new map describing this updated shape. The specific order in which you add properties dictates the exact transition path. This transition chain is fragile. Using the delete operator to remove a property breaks the chain completely. The engine is forced to abandon the map structure, dropping the object back into slow, dictionary mode hash lookups. Object shape stability dictates raw execution speed. If developers consistently initialize properties in the exact same order, V8 can execute dynamic JavaScript with the mechanical efficiency of a static language. Building maps solves the memory layout, but the engine still needs to know which specific maps are interacting with particular sections of your code. V8 embeds observation points directly into the executing code, known as inline caches. Every time a property is accessed, the inline cache inspects the object and records its specific map. These observations are logged into a persistent per-function array called the feedback vector. This is the database of runtime behavior that the optimizing JIT compilers will later consume. If an inline cache site only ever observes a single object shape, it enters a monomorphic state. This is the ideal scenario, allowing the JIT compiler to generate a fast execution path with just a single type check. But if a function is passed several different types of objects, the site becomes polymorphic, forcing the engine to cycle through multiple checks. If it encounters more than 4 distinct shapes, it hits the megamorphic state. At this threshold, V8 abandons local inline caching entirely. It falls off the megamorphic cliff, giving up on optimizing that specific site and reverting to a slow, global hash table search. The entire architecture relies on the strict predictability of types. V8 assumes your future code will behave identically to your past code, using the feedback vector as the exact ledger to place speculative bets. Those runtime observations feed a 4-tier compilation pipeline. Code moves from ignition to sparkplug, then up to maglev, and finally into turbofan. Functions graduate through these tiers based strictly on their execution frequency, or heat. The engine spends more CPU time analyzing and compiling hot functions, trading that upfront compilation cost for drastically lower execution times. For the most frequently executed code, turbofan takes over. It performs heavy, aggressive optimizations like escape analysis and loop unrolling to strip away virtual machine overhead. Turbofan achieves near-native speed by generating speculative machine code. It looks at the shapes recorded in the feedback vector and compiles instructions that assume all incoming data will perfectly match those exact profiles. But data in JavaScript can change without warning. If Turbofan generates highly optimized code for processing small integers and suddenly receives a string instead, that speculative assumption fails. This triggers immediate deoptimization. To recover, the engine must perform a frame translation. It captures the exact state of the optimized CPU registers, translates those values back into the interpreter stack layout, and seamlessly resumes execution back in ignition. Deoptimization is the critical safety net that makes the whole JIT system work. It allows Turbofan to optimize ruthlessly without having to worry about generating incorrect mathematical results. V8 doesn't achieve high performance by making perfectly safe compilations. It reaches native speed precisely because it has an infallible bailout mechanism for when its aggressive speculations are wrong. Even the fastest execution generates waste. To manage this, V8 uses Orinoco, a garbage collection system engineered to reclaim memory while keeping the main execution thread completely free of interruptions. Orinoco's architecture is based on the generational hypothesis, a statistical law of memory behavior, stating that the vast majority of allocated objects die almost immediately. Following this hypothesis, Orinoco targets the young generation memory pool frequently. It uses a parallel scavenge algorithm that ignores dead objects completely and simply copies the few surviving objects over to a new memory space using multiple background threads. For the rare objects that survive long enough to reach the old generation, Orinoco deploys a concurrent mark, sweep, and compact strategy. This heavy traversal happens almost entirely in the background, preventing the application UI from freezing. Every part of the engine acts as a single cohesive loop. The scanner and parser structure the raw code. Ignition executes it while inline caches watch the shapes. Turbofan accelerates the predictable paths, and Orinoco cleans up the resulting memory. V8's power is rooted in constant observation. It accepts the dynamic nature of JavaScript, tracks the patterns hidden inside the code, and relentlessly optimizes for the most